record. There we go. We got the story going. So welcome back, everybody. I was just saying that I have homework 0 downloaded. Happy to see that everyone was able to complete it. Got your 3 points of extra credit ready to go. Homework 1 is not yet available, but I hope to have that up by the end of the week. I will shoot you an email as soon as it is available. It's not due for 2 weeks, though. What is due next week is your first formative assessment, number 1. That's an icon, so it is under quizzes in icon or assignments, one of the two. I think you can get there either way. The idea is to give you an opportunity for structured review. So it's worth 2 points whether you complete it or not. I want you to complete it, I should say, whether you complete it accurately or not. I will look over the answers Tuesday morning, and then we'll go over the results in class. That way, if there's any questions or points of misconception, I can address those as we move forward. So you can help yourself to that whenever you are able to get to it. Let's see here. We have Lecture 3, Example 3A, and Example 3B to do today. But let me give you a better background. Isn't that better? That's a better picture to stare at to start with. Someplace we wish we were, rather than the land of snow and ice. Oh, February. February is the worst. But we are going to make it through. So what do you remember, as you're staring at the beach here, about last time? As usual, I will take words, gestures, letters, text in the chat box, whatever you feel like. What did we start talking about last time? Oh, we have some letters. Yes, 2 piles of variance. Yeah, the idea that in longitudinal data, at a minimum, we have sampled multiple people, so they're not going to be the same. And we've sampled multiple occasions, and they're not going to be the same. So at a minimum, we have 2 piles of variance. Pilesofvariance.com, yes, that is my domain. That's my shtick for teaching this material. So piles of variance, I think, is a useful, concrete way of thinking about these things. We have letters that go with them. So U sub 0 and E sub IT or TI, it looks like, yes. So the idea of U corresponds to level 2. The idea of E corresponds to level 1. We'll review those in just a second. Let me catch up on the rest of the messages here. Question, is it true that U0I, which is known as a random intercept, is affected by the time invariant fixed effects, while ETI, which is level 1 residual, is affected by time varying fixed effects? Not quite the right words, but yes. So fixed effects of time invariant predictors or fixed effects of time varying predictors, that is true. So if we go back over the vocabulary, we have level 2 is between persons, is time invariant, and level 2 variance in the mean, in particular, one pile we know of as level 2 random intercept variance. So the variance of the U sub 0 terms, going to have to get my picture out here. I want this picture right here. This is slide 11 in lecture 3. So the idea that people are different from each other on average. So U0I is how far off each person's mean is from the grand mean. So why do people have different means? Why are some people higher or lower all the time? That would be explained by fixed effects of time invariant level 2 between person cross-sectional predictors, inter-individual differences, as it were. Whereas within a person, so once you pick up your U0 and get down to your person mean, ETI picks up what's left. Why are you off your mean today? So why is today different than yesterday? Why is this year different than last year? That's E level 1 within person residual variance, intra-individual differences, the part that only longitudinal data can get you. And those differences in the outcome are explained by time varying predictors. So predictors that also are measured at each occasion can explain why some outcomes are higher or lower at particular occasions. So yes, indeed. Yeah, we don't need subscripts in the chat window. That's fine. Where can we find the Word document with the examples? I don't have the Word document posted. I only have the PDF posted so that the formatting stays consistent. But within most PDF documents, you can convert it into either a Word document or the original file format. So you can probably do that on your end if you want, but then sometimes the equations and the annotations get sort of out of order. So I do the PDF so that the formatting stays consistent no matter who is viewing it. All right, I think I've caught up with that. Good work, everybody, so far. Do you remember? I don't know if we've really gotten into this yet. Actually, we haven't really emphasized this yet. But the idea of equations that go with this picture is slide 12. So subscripts in this class are everything. Keeping track of what's a constant and what's a variable, and for the variables, what it varies over. That is the job of subscripts. So if I have a cross-sectional model, 1y per person means 1e residual per person. These are both empty models because I have no predictors. So beta 0 is the grand mean for this cross-sectional example. The addition to it that we started talking about last time then is the u0. So beta 0 is the fixed intercept, the grand mean, the mean of the means. U0 is how far off your intercept is from the grand mean. So random effects are always phrased as deviations. Fixed is the middle, random is how far off. So if my U0 is positive, that means my mean is higher than the grand mean. And then these two together get you to where your person mean is. From there, ETI, E for each time for each individual person, gets you to where your outcome is at that occasion. So we have YTI and ETI that are per time per individual. So one outcome per occasion per person. The data structure is set up that way. So it's one row per outcome per person. U sub 0, it's sub 0 to go with beta 0. So that's the idea that this is an intercept. It gets an I because each person gets their own U. So U is a person thing. And then once we add predictors, so this sort of idea here, the predictors that are person level, that are measured once, predict the U variance. So the random intercept variance at level 2 is the U variance. And then the predictors that are measured per occasion predict the E variance, the residual variance at level 1. So this is the aforementioned regression lasagna. Do you remember that? The one thing that I know how to cook, and that's it, is the lasagna recipe that I stole from the restaurant I worked at. You have your level 2 lasagna and your level 1 lasagna, right? So we have time invariant things that predict the U variance at level 2, time varying things that predict the E variance at level 1. And then we started looking at an example of what happens to the test of the fixed effects when you have a U included versus when you don't. And I think that was about where we started. We introduced the setup for this example last time, the code to stack the data into one row per occasion per person, and to create predictor variables that are dummy coded. So I have time 1 as a predictor where 0 is a pretest and 1 is a post-test, and I have 0 is control and 1 is treatment for my grouping variable. And so I think we had gone through this much code and the descriptives, and we were ready to start modeling maybe. Is that about right? Does that sound about right? Okay. Any other questions or things you want to talk about before we jump back in? Cheers. I have a package of new straws coming today in Amazon I'm very excited about because that is what passes for excitement in February of quarantine. A question relating to time. Okay, what's the question? If it isn't like pre-test, post-test, what is it like? Repeated measures of arrest in your example, like how many times they got arrested. Repeated measures can be any number of occasions. So 2 is the minimum to call it repeated, but these concepts and the modeling strategies apply no matter how many repeated occasions that you have. The differences have to do with how you can expect the occasions to be related to each other changes if they're far apart in time versus if they're very close in time. And so there's two main sort of families or approaches of longitudinal models. I distinguish within person change from within person fluctuation in terms of the concerns that you'd have given the way the data have been collected in the design. But this idea of between person versus within person permeates all of that. So that is a general concept. Do you have to create a time variable that counts the occasions? Yes, you do need to have an ID variable for occasion in the same way that you have an ID variable for person. And you actually are going to need two ID variables for occasion because in the code, at least in SAS, one of them is treated as a ID variable and one of them is treated as a predictor. So for the ID variable, it can just be like time 1, time 2, time 3. For the variable that goes into the model as a predictor, it would keep track of the actual distances in time. So this is 3 months later, this is 3.5 months later, this is 4 months later, that kind of thing. You don't want to round them into convenient intervals because that's not helpful in the analysis. So you would have an ID variable that's ordinal and an ID variable that keeps track of exact time as two separate columns. Okay, I think I'm caught up with the chats. Other questions before we jump back in? All right, so my purpose here then is to introduce you to the model code that we will use throughout the semester in SAS and Stata mixed. And what it's going to look like in R is going to change across my examples because in R, one package does not do all the things that I need it to. So I am learning more about the Wild West that is R, much to my dismay. But this model right here is where we are starting. This is the simplest possible model you could ever have. There's nothing in it. All it does is take your outcome variable and give it a mean and give it a leftover variance around that. So at this point, it's all the variance that's in Y and it's all in one pile. So I'll show you what happens then in terms of how you specify the code to change that and what happens in terms of the parameters that are estimated as you add things to the model for the variance as well as the model for the means. So fixed effects of predictors go in the model for the means. Piles of variance, random intercepts, and residuals go into the model for the variance. So in SAS, the command is proc mixed. My ID variables go on this class statement. So level 2 ID is person ID in this data set. Level 1 ID is the original version of time. On the model line, I have Y equals and then my predictors. This is an empty model, meaning I have no predictors. And so I don't have anything there, just the options in terms of what I want to see for the output. We'll talk more about degrees of freedom later on. You can ignore that for the time being. The repeated line is how we tell SAS how the data are structured, which rows go with the same person. So in this case, time is the level 1 ID variable. It's just time 1 versus time 2. And person ID is the level 2 variable that organizes which rows belong to the same person. R and R core are requests to print what the model predicts the variances and covariances across time are going to be. And the type that we've requested, this is known as VC or variance components, meaning no extra anything besides just E. So this structure is known as an identity matrix in stats terms. It says that the residual variance is equal across all observations with no covariance whatsoever. This is general linear models. That's what E is. So you've actually been making a choice as to what E is in those models without even mentioning it, because that is a default. If you don't have this line in here, that's what you get. And then run, of course, makes it go. In mixed, same beginning structure, Y is here, Any predictors would go right after it. Since there's none there, that means it's an empty model. The 3 slashes is a line continuer because Stata doesn't use semicolons, and so it thinks when you get to the end of a physical line of code that that command is over, and if you want it to keep reading, you have to do these line continuers. The nesting structure for mixed and Stata is this bar or pipe, and the variable. And by default, it puts in a random intercept. I don't want that in yet, and so I've put in no constant. And residuals independent over time is the analog to type equals VC in SAS. And I'm asking it to use residual degrees of freedom, which is what it insists for this model, and to get other information based on the model fit statistics, which we haven't talked about yet, but which is coming. All right. Any questions on the code up to that point? Okay, our folks, today we are in GLS, which stands for Generalized Least Squares, and that is because only GLS will let me have different patterns of correlation across the occasions without necessarily random effects. So the way that I am specifying this model is by putting all of the variance and covariance into one matrix, even though it's going to be in 2 piles. So I am naming an object that saves all of the R output from this function. Model is outcome, and then the tilde is actually the equal sign with a 1, meaning I just have a fixed intercept. And correlation equals null means I have no correlation between the e's. The e's have a homogeneous variance across all observations by default. And to change that, there's actually another command that we will use in the next example. And then to make it actually print the results, you have to use summary. So correlation equals null corresponds to residuals independent, corresponds to type equals VC, which is all that right here. All right, so as I told you before, my plan is to show SAS output in the handouts and to annotate that. However, there are text documents for Stata output and for R output inside the zip folder that has all of the data files so that you can follow along with those and take notes in those if you so choose. So the first thing that SAS is going to tell you is how it understands your data structure to be. Check this first, because if SAS didn't read your data incorrectly, game over. That's step 1. So number of covariance parameters is the number of terms in your model for the variance. Right now we have E. It has a variance, and that's what the 1 is. Columns in X is the number of fixed effects. We have 1. We have a fixed intercept. Z is going to be number of random effects that are in a separate matrix. We get to those next week. We don't have those yet. And then it understands that we have 50 observations for level 2 people, each measured up to 2 times. So this is a pre-test, post-test example just to get us started in the world of longitudinal data. So this thing right here is what's called an R matrix. This is the model predicted variance and covariance at each occasion. So what this model says is that at pretest, the variance of this outcome is about 40, and it is exactly the same variance that is predicted at post-test. So this is what the model says should happen. Where we're eventually going to go with this, by the way, is to compare what the model says should happen to what actually happened in the data. Those of you who have taken SEM with me, this will sound familiar because I'm talking about testing model fit. It's the exact same set of concerns. So this is a prediction. This model predicts the same total amount of variability at pretest as at post-test. And the key thing that I want to point out to you is actually this blank space. That blank space is important. That blank space is where a covariance would go. The fact that it is blank means the model says there isn't any. It says that the pre-test scores and the post-test scores have nothing in common. That is unlikely to be the case, but that is what an E-only model says, is that we have independent observations. even pretest and post-test from the same person are predicted to be independent. So we know this is going to be wrong. I'm showing this to you for pedagogical purposes and also as a comparison to see what happens when we fit the right model. This covariance matrix, as it is called, gets turned into a correlation version, which is standardized. And so each of the variances is standardized to 1, and whatever the covariance would be in here is going to be standardized to become a correlation. So in the next model, we'll see actual values there for what the predicted correlation between occasions is supposed to be. Next up is a table that lists all of the parameters in the model for the variance. So the name of this table is covariance parameters, which is not a great name because it should be variance and covariance parameters. It's a bad name. But if SAS output were transparent and easy to read, I would not have a job. So it's covariance parameters, but they mean variances too. And this is just going to be a list of all of the parameters that you've asked for in your model. And all we've asked for at this point is E, going up here again, that thing. We want its variance across all observations, people, and occasions. So that's my 40. So that term right there, that 40, that is what we used to call mean square error or mean square residual. That is our residual variance. Given that we have no predictors in this empty model, it's all the variance in the outcome. So 40 is as much variance as we have over occasions and persons. Unlike sums of squares land, we also get a standard error for our variance. So that's something new. Because yeah, those are not always going to be the same across samples. So a standard error is meant to describe how far off on average the sample whatever is from the population whatever. In this case, it's the sample variance from the population variance. However, SAS is super helpful to you and tries to give you a hypothesis test about this variance being different than 0. You are never, ever, ever, ever allowed to look at those. They give them to you, but there's never, ever, ever. The reason is that variances can't be negative. So trying to test a null hypothesis of a variance being not 0, assuming a two-sided sampling distribution when half of it literally can't be there, can't work. So I will teach you another way to test whether or not a variance term is needed in the model, whether it's greater than 0, via likelihood ratio tests, which some of you probably have already heard of. This thing right here is not relevant yet because it tests what else you have in the model for the variance besides E. Right now we don't have anything else in the model, so there's nothing to test. This table is model fit. We'll get to that later. We can ignore it for now. And then last but not least, this is the solution for the fixed effects. Now that is a good name. That is a list of all of the fixed effects that you have asked for. Fixed effects go in the model for the means. They describe either fixed intercepts or fixed slopes of predictors. Right now, all I've got is an intercept. Given that I have no predictors, this intercept is the grand mean. So on average, this outcome has a mean of 53. I have a standard error for it, standard error of the mean, as we would know, and it gives me a hypothesis test as to whether that outcome is different than 0, which in this case is not terribly useful. Okay, how are we doing so far? Okay. All right, now we're going to add another pile. Ooh, I like the thumbs. Thank you, black box people. I appreciate it. New model. So I'm on page 4 here. Let me make this a little bigger. So I have added a random intercept. I have added a term to the model for the variance. I have not added any predictors. So what I am asking it to do is to take what we were calling just one pile that was 40 and split it into two pieces. How much of the 40 is because some people have a higher mean than other people? That part is my U0 variance. And then after controlling for person mean differences, how much variance is because some occasions are higher than others, so differences between pre-test and post-test. That part is E. So the name of this structure, for those of you who've had formal classwork in repeated measures ANOVA, this structure is called compound symmetry. That is a stats term, and that is right here. So those tiny two letters are the only difference in the SAS code between this model and the previous one, going from VC to CS, compound symmetry. Compound symmetry in Stata is exchangeable. Fun with synonyms. Compound symmetry in R is comp sim. R is trying to do you a solid, right? Not just acronyms, but comp sim, you know, compound symmetry. So that's the difference in the code. We are taking what was one pile of E residual variance and splitting it into two. That's what we're doing. So when I get to the output, now I have two parameters in the model for the variance. I've got a U variance at level 2 and an E variance at level 1. My little R matrix here still has 40-ish on the diagonals. So what's being shown row 1, column 1, and row 2, column 2? That's what the model says the total variance is at pre-test. That's row 1, column 1, and post-test, row 2, column 2. The model says it's the same. The model also says, though, that that total is because of two different piles. How much of it is E and how much of it is U? So those two numbers are given to us in the covariance parameter estimates table, the 12 and the 28. The CS term, that's your random intercept variance. The 12 is the amount of variance in this outcome due to person mean differences. The 28 is the amount of variance due to differences between pretest and posttest after controlling for person mean differences. So you put the 12 and the 28 together, you get the 40. So we've made two piles, but when they're recombined, it's about the same as what it was before. So that might make you think, well, then why are we bothering? We are bothering for this. This is the magic. The 12 and the corresponding correlation of 0.3. Do you remember what used to be there in the previous model? No? This is a gesture question. Nothing! Yeah, I would also accept goose egg hands, 0 hands. I'm not sure how to make blank with a hand, but 0 and blank are interchangeable in this. Yeah. Nothing was there before, and now there's something. More specifically, this model says that there is a covariance between occasions. Now, covariance is in unstandardized units, and so you can look at this and be like, okay, 12, is that a lot? Well, I can tell you it's a positive number. So if you're higher at pretest, you're probably higher at posttest. But to put that into terms I understand better, I can standardize that 12, and that's shown in the correlation metric instead of covariance down here, the 0.3. That 0.3 correlation has a special name, ICC, intraclass correlation. question, two questions. Will I repeat what the 28 is again? Yes. The 28 is the variance of the level 1 ease, the within person variance. So yeah, the 28 is the variance that is within persons at level 1 over time from pretest to posttest. Level 2 is the 12. That is between persons due to mean differences due to the random intercept that is actually cross-sectional. And if I take 12 over 40, I get my 0.3 intraclass correlation. Can I say the estimate of the CS line is between persons variances and the residual line is within persons variances? Yes, 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 you can. Indeed. So that 0.3 then, you can talk about this in one of two ways. You can talk about it as a proportion, or you can talk about it as a correlation. If I go proportion, what I'm saying is that of all the reasons why there's differences in this outcome over times and over persons, 30% of that is because of which person is which. 30% of that is cross-sectional, would have had it even if you had measured them only one time. The other 70% is within persons over time. So 30% is at level 2 between persons, 70% is at level 1 within persons. The other way you can talk about it is pretest is correlated with posttest at 0.3. Either way, it ain't zero though. And I know that it ain't zero because I actually get a hypothesis test built in for that. So we will talk more about this next time, but this is a likelihood ratio test. It is the difference in -2 log likelihood for the previous model relative to this one. And that is how we test whether or not we need variance terms or covariance terms in the model for the variance. We will talk more about that next time. But you can probably eyeball it though and go, yeah, I think 0.3 is probably not zero. And we have the same fixed intercept of 53 as before because we have not changed the model for the means. But the standard error has changed. The standard error for our mean used to be 0.63, and now it's 0.73. And that's because previously we were thinking of this as 100 independent observations. Now we're thinking of it as 50 observations of 2 occasions each. So that dependency reduces the amount of information that we have. It makes the standard error higher. Okay. Any of that you want to hear again or ask me questions about? We're good? Good?
I have a question.
Yeah.
Okay, so the R matrix for the base model where
Mm-hmm.
we didn't have, where we just had one error term, right? So the variance in the diagonal in that one, was that like the residual variance, like the overall variance?
Yeah.
Yeah, this one, 7.3334.
Mm-hmm. Yeah, if you just estimated the variance of this variable, that's what you would get.
Okay, got
Mm-hmm.
it. And it's the same for pre and post test?
The model says it is. So
Okay,
if this is more like an average of the two.
got it, got it. Thank you.
Yeah, yes. And none of the predictors are in the model yet, and so we don't have like the right answer in terms of how I simulated the data, but this is what the model says. And so what we have done in creating two piles of variance, two piles of variance are a way to introduce a correlation into the residuals from the same person. That is what it is for. In other words, we have built in dependency into our model. We don't have independent observations, we have dependent observations. Occasions from the same person are correlated. So we build that in. We let them be correlated, and then we go about our business. So let's go about our business and add in some predictors. So I am adding in 3 more fixed effects in addition to my fixed intercept, so 4 total. I have a main effective time, so whether it's pre-test or post-test. I have a main effective group, whether it's control is the 0 or treatment is the 1, and I have their interaction. So I'm asking whether or not people who are in the treatment group improved more between pre-test and post-test. That's sort of the definition of what you would look for in these sorts of randomized experiments. You want to show that relative to whatever maturation or change would already have happened in the control group, that whatever you did changed that change. So the interaction term is the key to group differences and change. So I have here the logic by which I'm going to ask for all possible cell means, as you would call them, combinations of pretest by group. So how the model says I would get each of these 4 combinations, as well as the simple effects. How the model says I would get what the effective time is for each group, as well as what the effective group is for each occasion, because only some of these are given by the model. This, what I called the main effective time, is a conditional main effect. That is the difference between how post-test differs from pre-test, specifically when the interacting variable of group is 0. So what that means is that beta 1 is the effective time in the control group. Beta 3 is going to tell me how the effective time differs in the treatment group. To get to what it is in the treatment group, I got to add them together. So beta 1 plus beta 3 gives me the effective time in the treatment group. Likewise, that beta 2 right there is how treatment differs from control. But given the interaction term, it's how treatment differs from control at pretest. The interaction then talks about how treatment differs from control differently at post-test. I have yet to figure out how to write the way that I speak, but I'm guessing that italics would have to be involved. Unfortunately, in APA style, they say not to use italics for emphasis, but I don't know how else to write how the treatment group differs differently without somehow setting that off, right? So yeah, how the treatment group differs from control differently at post-test, that's my interaction term. So to get all of the simple effects, we have our friends estimate statements in SAS. So if you haven't seen these before, I have some materials that went with lecture 2 I would recommend reviewing, but this is the first time that we've seen them in this class. So I am adding in my fixed effects here. So time 1 is centered such that 0 is pretest and 1 is post-test. Treatment is centered such that 0 is control and 1 is treatment. The interaction term between these, which you can define on the fly using an asterisk. I'm in this model going back to my E-only model. So 1 pile of variance that's going to be left over after these 3 effects are added. And then I'll show you what it looks like with 2 piles so we can see how the results differ. And then in these estimate statements, the word, like intercept here, refers to the beta. So let me try and get this all on one screen. So like control at pretest, the word refers to what the beta is going to be. So SAS estimates it, it then stores that in memory. The number that you put here is the multiplier that goes in parentheses. So what do you want the prediction for? Well, if I want it for the control group, then I only need beta 0 because for the control group, every other term would be zeroed out. Whereas, for instance, if I want the mean at treatment for post-test, that's when every other term becomes 1. And so I would pick up 1s in there. For the simple effects of time, I start with just the word time, which is actually referring to beta 1. And then for the interaction term, I plug in the modifier. Who do I want the effective time for with respect to treatment? If it's 0, I want the effective time for the control group. If it's 1, I want the effective time for treatment. Likewise, if I want the simple effects of treatment, then what I'm talking about is starting with 1 beta 2 at a minimum, and then at what occasion do I want the effective group? So if I want the effect of group at pretest, the modifier is 0. If I want it at post-test, the modifier is 1. So this will give me all of the information that I would potentially want to report. What is the mean for each possible condition? What are the differences between each possible condition with respect to the two predictors of interest? And then what's the interaction term? And I have included that as another line here just so that all of the numbers are in the same place in the output to make it easier to go through. Last but not least, the contrast line here. We don't get an F-test for our model by default anymore, like we used to in sums of squares land. So if you want that, gotta ask for it. So contrast is a way to lump together any set of fixed effects for which you want a joint test of whether they're 0. So I want to lump together beta 1, beta 2, and beta 3 and test them all at the same time. The commas indicate that I want to test separate effects to create more than 1 degrees of freedom for the numerator of the test, as opposed to somehow adding them or subtracting them. Question, can you explain what simple means? Does that mean at a specific level of treatment or time? Yes. Simple means conditional. I use that term because that was how I was first taught. And so that's kind of like my native language is to like slip back into that, even though it's not simple. But you also will see this in the literature, people talking about decomposing interactions by probing them and getting simple slopes. I hate the word probe, by the way. It makes me think of Cartman and the anal probes, like, everything, you guys, it's anal probe. Thank you very much. That's my best Cartman imitation. I believe the inaugural South Park episode featured an anal probe from an alien. But that's what I think of when I hear the word probe. So getting simple slopes means getting the effect of a predictor conditional on a level of the interacting predictor. There's nothing simple about it, though. But you can't call it a complex slope because I think that term's already taken. So does that help? So many words. I know, there's a lot of words that mean the same thing. Conditional, though, I think is a better word for it. You can't just say this is the effective time. Who is it the effective time for? Because the model says there's a different effective time for the control group versus the treatment group. So you got to be specific. Okay, Stata folks, your code looks almost exactly the same as what you would see in a general linear model. So I'm adding a C dot instead of my predictors so that I can use them in doing math later on. If I don't do that, it yells at me. Except for your interaction definer is either a hashtag if you are under 40 or a pound sign for those of us who are a little bit older. Take your pick. That's how you define interaction terms on the fly. And then the lincom statements here do the exact same thing as the estimates, but they show more explicitly what is actually happening. So for instance, C1 time times 0. C1 time is the beta. The multiplier in parentheses is the value that you want it for. And so then we add everything together with the pluses. Small, by the way, oh my God, if anyone from Stata Corporation is listening, can you please stop this? So I asked it to use degrees of freedom for the denominator in the estimation. In mixed, this is not a default. If you don't add that, you get t's and chi-squares assuming infinite, no, z's and chi-squares assuming infinite denominator degrees of freedom. For samples that are smaller, then you should have t's and f's instead. Okay, cool. You would think that since I asked for the analysis this way, that all of the follow-up things I want from said analysis would be done the same way. You would be wrong. Instead, if you want the accurate degrees of freedom used in the model, also used in all of these other things, you have to add the option small every single time. Yes, that face, T, I see your face. Yes, exactly. That was my reaction with a bit more profanity involved when I first figured this out. Because I'll go through and build all my examples and I'll be like, why aren't the results matching in SAS? And I'm like, oh, I forgot to small it. So you have to small all of these things to make it work, including your tests. So this is the analog of contrast, where I'm asking for the joint hypothesis test of all three fixed slopes, the F value for the model. I have to small that as well. Okay, so I know that this is sort of a lot of new code, but we'll get a chance to practice with it throughout the semester. Any questions on mixed in SAS or Stata up to this point? Okay. All right, R people, I hope you already know how to do this because it is not transparent, but I am picking up with this thing right here is a new command. Where is, oh, Jing, you helped me with this. Thank you very much for teaching me how to put the labels in. Giving you props. Yellow thumb, she says. So this is GLHT, which stands for General Linear Hypothesis Test. This is the analog to estimates or contrasts. You have to tell it your model that you wanted, and then give it the lists of the coefficients. And so these numbers refer to the betas in the model. So there's my 4, the intercept, main effective time, stop it, main effective treatment and interaction term, and the values are the multipliers in order. So a much more unfriendly way of doing this, because rather than having the words and the values interspersed so you can see what they mean, you just have to know the order in which they're listed. And then you can ask for that hypothesis test for all 3 in a separate statement and ask for the F value that goes with it. So I was able to at least figure out that much, although it got the degrees of freedom wrong and I had to fix that. So like I said, I'm not great at R. I'm still working my way through, but I was able to get the analysis correct, so there's that. So here's what we have then. So let's see, questions. Are correlations supposed to be null now? In this model, yes. So what we're going to do, scroll back up to where the model is. Stop. There it is. I'm adding predictors to the original one pile model right now. And then I'm going to do the same exact model, except have the random intercept in as well, so that you can see what the difference is in the results. So this is like a before and after comparison after adding predictors. So I know this is an inappropriate model because it assumes that pre-test and post-test are uncorrelated, but I want you to see what happens when you do that. Okay, thanks for the question. And this, by the way, is example 3A in the book. It is exactly these data and this set of analyses and the code on the website as well. So if you're looking for a little more explanation, you can read about that. So now my R matrix, what used to be 40 is down to 27. So yes, we have explained variability in this outcome. We've explained it by a fixed effective time, group, and their interaction. So that has accounted for some of the reasons why people are different from each other and occasions are different from each other. 27 is what's left. But because this is an E-only version of the model, one pile of variance, it says that pretest and posttest are uncorrelated. So independent observations, this is just a regular old linear regression. That's what this is. In mixed, but that's what this is. So here's my residual variance that's left, my 27. Here are my fixed effects in red, since that's my color scheme, red for the model for the means fixed effects, blue for variance things. This out here with the betas is me being nice. SAS does not label things for you. If it did, again, I would not have a job, so I'm kind of okay with it being obtuse. But if we roll through these interpretations real quick, 49 is my you are here reference sign for the model. Given the coding of these variables as to what 0 means, 49 is my expected outcome at pretest for the control group. Time 1, then, is the difference of how post-test compares to pretest. So post-test is higher on average by 5.8, ... What else do I have to add onto my sentence in order to make it correct? This is a conditional, simple effect. So 5.8 is the difference of post-test relative to pre-test for the control group, yes. So simple slope, simple main effect, conditional slope, all of those words reflect the idea that I can't just call this the effect of time and be done. It's the effect of time when the interaction term is 0, which is in the control group. Similarly, the simple main effect of treatment, conditional main effect of treatment, simple slope of treatment given by the model is specific to when the interacting time variable is 0. So this is the effect at pretest. 1.68 is the coefficient. If I scroll over to the last column here, P is greater than our traditional 0.05, so this would not be significant. Would this be good news or bad news if this were an experiment I were conducting? If treatment and control have a simple main effect that is non-significant, given the way I've set up the model, is this good news or bad news? Got one vote for good news? 2 votes, I see some nods. Yeah, this is at pretest, right? So I just found out that random assignment worked. Yay me. Control and treatment are equivalent to begin with. That is what I would hope to see. Interaction term then. Interaction terms do one of 4 things. They take their main effects and they make them more positive, more negative, or less negative. So if I start with the effect of time in the control group is 5.8. The interaction term says that effect of time that is positive is more positive by 2 in the treatment group. So if I put those together, the effect of time in the treatment group is about 7.8. It is more positive according to this result. And down here, I can actually get the result from my estimate statement so that I can get a hypothesis test for that effect. However, that 2 difference in the time slope of the treatment group relative to control is non-significant. So while treatment did improve more than control, it did not improve significantly more. The other way that I can think about it is the group difference at any occasion. The group difference favored the treatment group at pretest, 1.6. The group difference became stronger, in this case, more favoring the treatment group at post-test, but not significantly so. And if I want the group effect at post-test, I can ask for that, and that actually is significant. So the groups were Not different at pre-test. They are different at post-test, but they did not change differently. Question: what happens if the interaction is significant and the main effect is not? Which main effect? Because there's four that we could be talking about here. Dot, dot, dot. Time by treatment is significant and either of them. Well, that's fine. The reason that I'm making such a big deal out of this is to prevent people from accidentally over interpreting these things. This is good news that the treatment's simple effect is non-significant because it's at pretest. The model says it's going to be different at post-test because of the interaction term. So this is good news. Also, the fact that there is a significant group difference at post-test, what you get if you add 1.68 and 2 together, the fact that that combined term is significant would be good news, which means at post-test, the treatment group is greater than the control group. It's just that they did not change differently. According to this model, though, is this model likely to be correct? No, it's not, because of this blank spot right here. That blank spot is the problem. This model has only one pile of variance, only one E at the end of my equation 3 pages ago. There it is. That means we're saying that the post-test and pre-test observations are unrelated after we control for all these predictors. That is unlikely to be the case. It's a testable hypothesis. So let's see what happens when we fix it. Our new friend, U0. We've added a random intercept. We've split our residual variance into that which is between persons, U0, level 2, random intercept, and that which is within persons, E, level 1, within persons, residual. So it's tricky because residual used to mean just leftover, and now it's like residual at level 1 because it's leftover level 1. So I'm going to try and stay away from the term residual and say leftover. E is the leftover level 1 residual variance. U is representing the leftover level 2 between person random intercept variance. All of the code looks exactly the same, except those two letters. CS, back to compound symmetry. Exchangeable in Stata. That will make more sense in our next example, by the way. When we have 6 occasions, you will see that exchangeable means all the covariances are the same and all the variances are the same. And in our land, we're back to core comp sim as a structure that's built in. So here's what we get. Our R matrix now has been fixed. The total amount of leftover variance is about the same. It's 27 according to this model, but there's a big leftover covariance. And if I translate that leftover covariance into a correlation, it's big. So after controlling for which occasion it is, which group you're in, and their interaction, the pre-test residuals and the post-test residuals are correlated 0.84. That ain't zero. That's going to happen in longitudinal data a lot of the time. You would expect very strong intra-class correlations in most applications. Not quite that big, but at least over 0.3 or so. So what has happened is that we still have a lot of random intercept variance left. It's 22. It's actually more than it used to be. The reason for that I'll explain in another week or two, maybe more. And residual is down to 4. So of the two piles, they've been explained differentially. There is relatively more between person variance left than residual within person variance. And so I have the two solutions for fixed effects next to each other. The one that's highlighted is the one from before. The one that is down here is the one that we just got with the correct intraclass correlation included. So I want you to take a moment and stare at these numbers. Estimates, same or different? Do a thumbs up for same, thumbs down for different. Same. Is that surprising? It's not surprising to me because they are the same model. The model for the means is exactly the same. We have said the same 4 fixed effects predict this outcome. Only the model for the variance has changed. Exactly. And what does the model for the variance do? It gives you your standard errors. Now let's look at what happened in particular. This one is the same because that is a level 2 predictor. So in forming the standard error for that predictor, the numerator of any standard error is some kind of variance left over. For level 2 predictors, it has to be both between person level 2 variance left over and within person level 1 residual variance left over. So all the variance left over goes in. That's why this is the same. Same thing with the intercept, which is treated as a level 2 predictor because it's based on that one cell. If I look at the simple main effect of time, and if I look at the interaction term, their standard errors are very different. Because what goes into the numerator before, when there was only one pile, was all the variance put together. What goes into the standard errors numerator after is just the pile that it should have explained, which is level 1 residual. So that has the result of, look at this. Look, it's been fixed. The interaction term is significant. Paying attention to the model for the variance actually helped in this case. So in practice, messing up the model for the variance by saying that you have independent observations when they're actually related to each other, it can actually hurt you or help you depending on which level of the predictor you're at. For level 2 predictors, it can actually make it better because it's a difference in degrees of freedom. Level 2 degrees of freedom versus total. For level 1 predictors, the results are better after controlling for the dependency because the part of the variance that's irrelevant no longer contributes to the standard error. So the effective time here is differences between pre-test and post-test. That has nothing to do with mean differences between persons. So mean differences between persons, which we've partialed out into a separate pile, don't contribute to that test anymore, and they shouldn't. It's irrelevant. So we end up with a different inference because standard errors come from the model for the variance. So even if you don't really care how many piles you need, if that's not a direct answer to a question you have, this is why we care. This is why we care. And the same thing happens if you have 2 levels of data, but you actually need 3. So if I had time within student within school, and I only controlled for student and not school, same problems. Standard errors would be wrong for the piles that are missing. Okay, how are we doing? So I want to ask you one more set of questions if we look at this equation again. Another way to think about repeated measures designs like this one is that you are introducing person as another factor of the design. So in analysis of variance language, the fact that we have 2 occasions and 2 groups, we would call this like a 2 by 2 ANOVA, 2 factors each with 2 levels. But actually this is a 3-way ANOVA because we have 50 persons by 2 groups by 2 occasions. So if we think about it from a three-way ANOVA kind of perspective, that means that we have potentially three main effects, one for time, one for group, one for person. We have three two-way interactions, time by group, time by person, group by person, and we have a three-way interaction. So I want you to look at this equation and help me figure out which one of these are here and which one of these are not here. So let's start with the main effects. Do we have a main effect of time? Simple main effect or conditional main effect, but whatever. Do we have one of those in there? Yeah, it's right here. Do we have a main effect of group? Yeah, that's right here. Do we have a main effect of person? This is a tricky one. What do you think? The answer is yes, we do. It's right here. That's my main effect of person. It's a random effect, not a fixed effect. The betas are fixed effects. I get a specific inference about each occasion being different from each other occasion and each group being different from each other group. I don't get the same type of inference from including person here. I don't get, is person 1 different than person 2? Is person 3 different than person 1? I don't get that. I don't want that. What I get is a variance across people. How much of the total variability is because people differ? That idea is what U0 is getting me. It's a random effect of person. So it is a person main effect. Likewise, if we go through the two-way interactions, here's one of them, time by treatment. Given this design, can I have person by group? If each person is in only one group, can I have person by group? Yeah, not if each person is in only one group. I can't have person by group because that would be, how does the same person respond differently when they're treated versus when they're in control? And that's not possible given my design. So if person by group is not possible, person by time by group is not possible. So that leaves person by time as the only other thing we could include. Is that here or is that not here? Person by time interaction. Do I have it or do I not? Oh, we got a variety of answers here. The answer is yes. It's right there. Person by time is E. I know that's crazy to think about it that way, but that's all that's left. E is, why did somebody change differently from pre-test to post-test, even after I control for which group they're in? So let me show you a picture about what I'm talking about. This is slide 16. So in two occasion data, I can either say this on the left, which is what I have. So this is a picture of everybody within the same group. So people from the same group have the same age slope. They get a different random intercept, so they are allowed to shift on the y-axis. And they have a residual, so that each occasion can be different than what is predicted based on their group. So I can either do it like this, or I can do it like this, where no, it's not that people have residual variance left over, it's that they need their own slope. And once I give people these non-parallel lines, I don't need E anymore. So either I have a person by time interaction, which is the picture on the right here. This is going to be the idea of a random effect of time, by the way, the idea that each person needs their own version of the effect of time, a random slope for time. I can either have that, Or I can say everybody changes the same, but there's some unexplained variance left over. In two occasion data, you cannot distinguish these two possibilities. So that is why for the rest of the semester, basically, if you only have pre-test, post-test, I got nothing for you. This is it. This is as fun as it gets. You could let the residual variance differ at each occasion, but you can't do anything random beyond the intercept because you don't have enough information per person to pull it apart. And any models that you have seen in an SEM framework, by the way, that claim to get latent differences out of two occasion data, the way they do that is by shutting off residual variance and pushing all of that up to the change score, latent factor. SEM does not fix it. So in two occasion data, you either have residual variance or you have individual differences in change with no error left over. I think the former is a little bit easier to justify. So that's where we're at. There. How is that, folks? Mind blown, I know. It's hard to think of an interaction or a residual term as an interaction, but that is what it means in this case. So that's not always the case, but this is what it is here. So big picture though, the idea of taking one source of variability and carving it up into two piles. It matches the idea of the design. We have sampling that differences between people, we have sampling differences over time. But the reason to do it, the reason that that matters in practice is right there. That idea of allowing dependency, allowing a relationship between the residuals from the same person, that gives us the right hypothesis tests for the fixed effects that we care about because that affects the standard errors. So that's why we pile things separately. How many piles are needed are based on your design. So if you have three different sources of sampling, if you have children over time from multiple schools, then you have three piles of variance. You'd have a school source of variance, a student source of variance, and a time source of variance at a minimum. So we'll talk starting next week about other things that you would have besides just random intercepts. That's where we're headed. All right. Questions before we adjourn? All right, then formative assessment number 1 is available for you to start working on. Your first homework is not yet available. I need to make sure that we'll have time to cover everything that's in it, so I'll let you know when that is available. Otherwise, office hours start now. Stay safe, stay warm, and come back on Thursday. So, bye everybody.